Okay, we'll see this version today. Will look a bit odd because I don't have my other tools set up, which otherwise are. Just give me 1 second. Okay, so you'll see this version today. Uh, so what we skipped over is there are a couple of things actually which I skipped over and I realized it late. One is let's talk about the PacBio sequencing. So it's good to see these things in. Okay, so the versions that you saw, I collapsed them both into the same version, doing saying that there's a power of those recommendations are not mine. Okay. So uh, yeah, full disclaimer: those recommendations are not mine. Okay, because I'm not logged in. Okay, so the reason we talked about this particular thing was to see that there is one molecule which often you have a choice of keep getting longer versus sequencing the same thing again. Then that was also one of the questions that was asked. So if you have two modes, if you have two versions, you can sequence it multiple times and you'll get high confidence version, which is also called the consensus or hi-fi. We very in a very shallow fashion we covered this, or you can actually keep going, but of course if you keep going also at some point you're going to hit the end, right? So in some sense it's better to go for this version where you don't have extremely long molecules, because then in principle you can keep going but your fidelity will, your accuracy will start to drop down. Okay, so this version is called the consensus sequencing. Okay, okay, so that was one video. um, the second version was this video that I missed. Oh, that's strange. Okay, that's okay. Let's just do why that is made private. This one. Okay, so that was a shorter version of the actual video, but hopefully you were able to get what it's trying to do. You have a nanopore, DNA goes through, current is generated, that current is read through, and then you eventually figure out what sequence it looks like. Right? Any questions about these two? This was our this was our second version of the third generation sequencing. Right, we saw its examples. One thing I skipped over is what's called the Ultima. The reason to talk about Ultima is because this came out, so this is as hot as it gets, right? Like whatever you're seeing here is extremely new. uh, I don't know which other courses in the country talk about something, but because just to keep up with this itself requires a lot of reading. So what you're seeing right now is an example of what's called Ultima sequencing. It came 4 years ago now, but in principle has been used in the last 2 years. The idea behind Ultima is inspired from, to some extent, inspired from both Iron Torrent and Illumina. We want to save money, and one way to save money is to save on the reagents, because that's what is going to cost a lot, right? So if you recall, in Illumina we had an onboard PCR, which is bridge amplification, which allows us to maximize uh, the throughput that you see in terms of signal. Here we try to get rid of it, and we say that I can anyway take care of amplification, so I can take my DNA fragments and I can amplify this outside without before throwing this on a chip. This is what a random chip of an Ultima or an Ultima flow system looks like. It's an open flow system, and you'll see this in just a bit of why this is an open flow system. The person who developed this had a mixed background in chemical engineering and material sciences, right? So this is where you use your engineering training to some extent. For each of this chip, what you have is you dispense the reagents. So you're still dispensing some reagents, but don't have to amplify. You don't have to have a super amount of amplification that you had to do in the case of, let's say, Illumina. You dispense your reagents here. You have kind of like a centrifuge, which will dispense it along the periphery. So each of this looks like a very simple silicon wafer chip. Once your material is here and it's dispensed over, you again start with your cycle. You load up again a lot of unlabeled versions and labeled versions of your bases. In each flow, so this is what your system is, in each time I will flow all the labeled versus the unlabeled version. So you will have, because you have multiple copies of each of these fragments, some of them will incorporate the labeled version, some of them will have the unlabeled version, right? Whenever you incorporate a labeled version, you will have again emittance of a signal. This is again based on fluorophore, and you can record this. The distinction between this and Illumina is here. You again you have all the A, C, G, and T's being incorporated. You again have a similar wash cycle, except this is happening at a much controlled rate, right? Which is allowing you to use lesser amount of reagents as compared to Illumina, where you would dispense the entire thing for a large set of molecules. Here, the amplification has already happened outside. You're looking at multiple DNA strands which are of similar nature, and then trying to figure out at each cycle which base gets incorporated, right? So the cycle here involves addition of one type of mostly natural. What is meant by mostly natural is you have most of them to be unlabeled and a very small portion of them which is labeled. So in most cases you will have continuation going on, but in some cases some of your molecules, so this molecule, if I have these copy of the molecules, if mostly I have, if this is the labeled version and this is the unlabeled version, you have more unlabeled versions flowing. So you will continue extending this without anything. But in some cases you will have, at each cycle, you will have a random incorporation of an unlabeled and let's say a labeled nucleotide. You can read what got incorporated. So for example, this could be A and this could be T, or it's also possible that I get an A here and I get an A here as well. It will become clear in the next slide. Then you do a wash again, and then you keep doing this in multiple cycles of the run. So just to give you more context of what is happening. So let's say here, these are all my similar strands of DNA which are stuck to the flow cell. When I start incorporation, I'm adding the labeled version and the unlabeled version. So in this cycle, I see an incorporation of 2Cs. The reason I can see 2C here is because when I'm flowing the DNA, so if I flow only one thing at a time, right? So if I flow only Cs and Cs, I can capture what is being incorporated because it will emit a particular signal. Here, so I flowed C and I saw this particular incorporation happen. Next, I flow, let's say A, and I see this incorporation happen. Here, among all the possibilities, you only see here you have an unlabeled version, so nothing happens. But here you see labeled versions being recorded. So it's only one A. But when it comes to here, you have three T's. So the sequence here was CC, triple T, and the signal that you got for each cycle is corresponds to the number of bases of that type being incorporated, such that each base has its own color. So blue, green, red, one kind of nucleotide flowing at a time, so you can record what gets incorporated. Does that idea make sense? Okay, so the reason this is important, so what will happen in case of homopolymers? So if I have a sequence like this, if I flow in at this cycle, if I flow in A, I don't see any signal. I flow T, I will see one signal because some molecule will take up the T. Next cycle, if I flow A, what happens? I will see incorporation here, 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 right? And I'll not see any incorporation for any other cycle. So as your number of bases increase, your incorporation of that particular nucleotide will also increase. What impact will it have on homopolymers? Is having homopolymers, which is molecules of this type or this type, is that good or is that bad? Is that a good thing to have here or is that a bad thing to have here? Correct. No, so you can keep replenish. You can assume that you can replenish it, and in this case, it's much more targeted. So you can assume that you have enough of them. But again, think of it from a technology point of view. Somebody has to read this signal, right? We do have that light problem, right? So we do have enough copies. So we do have that problem to some extent. So if I notice only one A, it's easier to tell me that there was only one A incorporated. But if I see multiple version, it's very hard to say whether it was 3 or it was 4 or it was 5, right? So if I notice, if I plot this signal strength across the homopolymer length, on the x-axis is a homopolymer length, on the y-axis is the unit intensity, you will start to see that beyond a homopolymer length of 8, this should keep going, right? The more homopolymers I have, I should keep seeing more intensity, but it starts to saturate around 8, which means that once I have 8 or more A's, T's or C's or G's, the amount of signal that I'm going to observe saturates. It's not going to be extra for me to be able to tell that it was actually a homopolymer of length 8, but it would just always, even if I have like 20, it will still count it as 8 or 10. So you're going to suffer at the homopolymer level. So that's why the error rate for when you have homopolymers is overall higher. This is the accuracy of the prediction. This becomes higher beyond a homopolymer length of 8. So if you have a lot of repeats or if you have a lot of homopolymers, they're slightly different things, but often repeats will have some particular motif being repeated. It will start to have lesser accuracy overall. Okay, so this is very similar to what we saw actually in the case of 454 and ion torrent, in terms of you have a cumulative or an analog signal per cycle, right? You're throwing one thing at a time, so you're able to measure what is going on. You have things under control. So there's one more version which tries to solve this homopolymer polymer problem. So everywhere we saw that homopolymers are going to be problematic, even in case of nanopore, whether it came from 8 or 10 or 12, it's hard to say. So that was solved by another platform which just came out. So Roche is trying to invent itself. by making an entry. So the Ion torrent that we saw was defunct in 2016, but in 2026, so this is as hot as it gets. This year it launched actually Leos 1, which is built on this new paradigm. So we saw SBS, sequencing by synthesis. We said optical based, right? So sequencing by optics, and now we have a sequencing by expansion, and this is extremely cool. I don't think it's intuitive. I don't think I would never have been able to think, and I think most people would not have been able to think how to get this to work. The key idea on this, which it works, is it says that the reason we suffer often is because these bases are very, very small. If you could somehow expand this, you will get the resolution that you require, right? If you make something bigger, it has enough capacity to emit even one light. If it emits, that is sufficient because it's so much of it coming out. And that's the key idea on which this is based. It uses the strand and extends it by a 50x length. This is called an expandomer, and it looks at the again the light being emitted from that expandomer. So just one base emitting 50 amounts of intensity is all you need in order to be able to sequence it. So let's see the video, and that will clarify what I'm talking about. Hopefully you'll realize that the innovation that is happening is at two levels. One is you have extended it, and then you're passing into the nanopore. Now if you pass this through the nanopore just like that, you will again run into the same issue, that how do I resolve when both of them are into the nanopore, that is it blue or is it red? For doing that, they have actually included this TCE, or the translocation control element, which uniquely identifies the signal and will help you slow down the entire read through process, so that you know at each point how much amount of current is being generated as this 50x molecule passes through, right? So innovation over innovation. One is expandomer, so you expand the base. The second one is have a TCE, which using nanopore, right? So this is mixing everything that we have done so far. You have the power of nanopore, So you can do long read, and then you have the power of being able to do an accurate nanopore, because now you've solved that problem of accuracy because you're doing one thing at a time. Okay. Any questions about any of this? That wraps up all the technologies that I wanted to discuss. There are few technologies that I've not talked about, um, which includes something called Element Biosciences Avanti platform, but they are, to some extent, it's just saving on the reagents. But these are the broad principles on which everything works, right? So just to revise Sanger sequencing, just look at fluorophore ACTGs, read them through. Then came next generation. You looked at the ion torrent, where you did emulsification. You added PCR reactions on the emulsifier. You looked at which signal is being emitted. The problem was it's going to be extremely slow. Then we added Illumina. Illumina started doing sequencing by synthesis by adding information about um, bases in a cleavable fashion. So you have a cleavable fluorophore. So you wash it and you read it again. And finally came these third generation set of sequencing, which either use a nanopore or a zero mode waveguide or an expandomer to look at real time sequencing. Okay, that's in just what we studied so far. Okay, so we'll go to just looking at what the sequencing data looks like. So any sequencing data that you turns out, irrespective of the platform that you're going, is going to be standardized in this format called FASTQ. So you had seen FASTA format. This is FASTQ. Q stands for quality. You will read a signal which would look like at. This is usually prefixed with at the rate of instrument or the read ID, what run number, which flow cell it came from, which lane it used, which tile it used, and so on. This is kind of specific for Illumina because that's where this is more or less relevant. But broadly, you will have a term which looks like at the rate some ID format. Okay, followed by sequence, followed by plus sign, and followed by this weird looking quality score. This is the ASCII version of the same sequence as to how confident this is, right? So the reason we are doing an ASCII is so that we can encode that quality in one simple character as compared to writing float values here. What does the quality score encode? So their most modern data sets will use a score of Phred, which is called a Phred score. If I add that score and add plus 33 to that number, we'll see an example and become clear. This is the ASCII character. So this is what is the quality or the Q score. We will define what a Q score is. If you add plus 33, this is the corresponding ASCII code that is encoded here, right? So for this, if I want to decipher what quality does it encode, I will subtract 33 from this. I will get the Q score, and from there I can get the quality of it. What is the Q score? The Q score or the quality score is 10 minus log to the base of 10 p. So it's a measure where p is a probability that that base call is incorrect. So you want this number to be small, which means if this is very, very small, it will be very hard to represent 0.00000001, right? The way you represent this is if you take a log 10, it will become, what is the log 10 of this? Yeah, minus 7, right? But it's hard to decipher minus values. It's unintuitive. So you add a minus to it and that becomes plus, right? So that becomes 10 minus log 10p. This will be a small number, so it's multiplied by 10 and then it becomes interpretable. So if this value is 10, that means there is a 1 in 10 chance that the base is incorrect. If this q value is 20, 1 in 100 chance. If this q value is 30, that means 1 in 1000 chance. Okay, this is just done so that we have nicer number here to interpret this. So q equal to 10, that's why you're multiplying it by 10, so that 1 in 10 chance that value is incorrect. Okay, is that clear? So if I see something like this, I can subtract 33 from it and get the corresponding q value. That q value, if this is a scale, this grows exponentially. So if q is 40, that is 1 in 10 to the power 4 chance of that particular base being incorrect. Okay. It's minus 10 log 10p. Sorry, I should correct that actually. It's also given. It's also often represented differently. It should be I will correct this. If actually right now it's on view only, but I will correct this because I'm not logged in. Okay, so it's minus 10 log 10 of p, not 10 minus log 10 of p. 10 times. So there's a star here. Okay. This is what an ASCII table looks like. So for example, if I get this, if I look at this up in my ASCII table, where is it? 60 something, 60, right? So this arrow stands here, 60. This is my score. I subtract 33 from it, I get 27, which is approximately 30. So 1 in 1000 chance of making an error. P will be approximately 1 in 1000. Okay. Okay. We'll also study something called what's called a SAM format, sequence alignment format. So once you map your raw sequencing data to a reference sequence, which we're going to talk about today, you have to represent how does the alignment look like. So in your assignment, in one of your new assignments, you will be looking at what does the alignment look like, and often we represent this as this, right, where you have an alignment happening. How do you store this information so that it can be very well read by a computer? We store this in a format which is called a SAM alignment format, or the sequence alignment map format. There is a bunch of things going on here that's not super important, but what this SAM file stores is where are you getting your read from, what format this is particularly stored on, what does the read look like. But the most important thing that you should focus on is how is the information stored here. So this is your coordinate and this is your reference sequence, what it looks like. Let's look at what does the alignment look like, right? So if I focus on one such alignment, this is the header section, this is your quality score of what does the quality of the alignment look like. We will talk about quality scores of the alignment itself, how good is the alignment. Then there are a bunch of flags here which are going to be overwhelming at this point, but focus on this particular section here. This represents how many mismatches or matches you get. So 8M stands for 8 mismatches, 2 insertions, 4 matches, 1 deletion, 3 matches. Okay, which means that if I take this particular sequence and I align it to the reference, it's already aligned. This is what I get, which can be summarized in the form of 8 matches, 2 insertions, and so on. So this is computer readable because once I input this particular thing and I tell it that what is the coordinate on which, so in this case, this is the position in the reference genome where it is aligning. So this alignment starts at position 7 and ends at position 30. Actually, no, this starts at 7 and it is of corresponding length. This is the position at which your next read starts or the next alignment starts, which is 30 base pairs below. But even if you know the start position and you know the matching string, you can figure out where it ends. But mostly you will store, all you need to store is where does it actually start, right? And this is the name of the reference sequence. This is which read it is coming from. We will see this a lot more in detail once we do the hands-on. But this is just to give you a preview of how you store the alignment format. Okay, there's bunch of fields there which are not going to be super important, but it's a very well thought out format. You store what is the name of the string, you store whether it's aligning or not, you store what is the name of the read. This is query, so this is the reference, this is the query. You store where is the position where your reference mapping starts. This is the quality of that score. This is called a cigar score. That is what you saw in terms of 8 mismatches, 3 deletions, and so on. This is, you can also store the reference name of the next read, which is at what position does the next read start to map. You can also store the position of the mate, which is the mate pair. If it is a read, if it is a paired end read, you can store where does the corresponding mate pair map. And then there are other scores which right now are not very important. You can store the quality score of the read. So there are two quality scores. One is the qual, which is the score of your read quality, and then there is something called the mapping score, which is this mapping quality. How good is your mapping overall? And we'll see how to calculate the mapping quality overall. Okay. Okay, there are multiple flags. Keep this in, of course, you'll never ask questions based on this, but keep this in your memory when you do your projects, it will be important. The most important flag that you will be, you care about is you don't want, ideally you would want only uh, a read which is mapping uniquely to one location. So SAM, while it's an alignment mapping format, will also store reads that don't map, but they will have a flag called 0x4. This is stored in hexadecimal base space. I would, for example, the first thing that I would do is I would remove all of 0x4 because these are not mapping, so there's no point keeping them into your disk, right? You can also look at whether it's a secondary alignment. Ideally, we will care only about primary alignments, which means that they are uniquely mapping. So you can remove all the secondary alignments because you don't care about them. It could also be marked as a PCR or an optical duplicate. So when we do mapping, we want to avoid, especially in the case of RNA, we don't want PCR duplicates. I will talk about this when we talk about RNA. But for this, right now, just keep into account that, keep into your memory that there are flags to tell you what each read is associated with. Is it mapping? Is it not mapping? Is it mapping only to one location or multiple locations? The secondary alignment is, so often if you start from a read R1 here, it can happen that, which we had talked about earlier, is maybe there is one portion where it aligns. So I'll just call it R1 dash. And there's another position where it aligns, R1 double dash. It's very hard to confidently say which of these two is it specifically aligning to. So one of them can become randomly a primary alignment and the other one will be a secondary alignment. So in this case, this particular thing is mapping to two locations, but I cannot resolve it. So I make one of them primary, the other one secondary. But since it is mapping to two locations, ideally I would not want to work with this because it's confusing. I don't exactly confidently know that where is it uniquely mapped. In an ideal case, you only want things like R2 or R dash, which only map here and nowhere else. Okay, only one location in the genome. So there's no confusion. Okay, the cigar has a full form. It's concise, idiosyncratic gapped alignment report. I always just call it cigar. It has a special meaning again. M stands for alignment match, and you can read the other things, but they are mostly intuitive. M, I, D are the main ones: alignment, insertion, or deletion. You can also do skipping, and you can also do something called padding and soft clipping, which will become clear. This will become clear once we talk about RNA. But just make sure that you understand right now that if I have to represent an alignment, so what should I write this as? What will be the cigar string for this? 2M, 2 matches, 1 I, 1 insertion, 1 match, right? So that's how you store this information. And good question. So it depends on whether I'm calling my reference, what is my reference, and so it's an insert. You store it with respect to the reference. So this is the cigar string for the query. So in this case, this was an insert. This was this will be deletion. Sorry. In this case, I will store it with respect to this. So this is a deletion. Sorry, this should be 1D and not 1I. Okay. If I switch, then it will become other thing. If I made this the query and this the reference, then the only thing that will change is now this is 1 insertion. So this will become 1I. Okay. Okay, we'll talk about the BAM format. So there's something called SAM format, which is the sequence alignment map format. But you will see that it's a lot of redundant information, which is hard. So one BAM file could be 4 GBs, 5 GBs, or 10 GBs, SAM file. I want to reduce the size of it. We can make a binary version of it and also make it indexable so that I can read it very, very fast. It will become clear what reading fast is in just few lectures down the line. But what I want you to know is there is some format in which you can use this to compress. This version is called BGZF or BGZF. This is a block compression implemented on top of your standard gzip conversion. This gzip compresses all of your information so that you store without losing information. You can store this in a much smaller file format. You must have all used gzip or tar gz or tar file, right? So when you tar your file, we will study what happens in next lecture. We'll study what does tarring actually do to your system. So gzip is just a random, just a way to store your, compress your entire sequence, right? So if this will become something of this format. When you tar something, it's done in a recursive fashion. So if I have a set of files, I can put them in a recursive format where rather than gzipping all of them individually, this entire block of information. So if I have multiple files like this, I can create a tar gzip of all of them at once. You're essentially individually running the gzip on all of them and storing them as one big blob of file rather than having to distribute 3 different files. So that is what usually tar gz is used for. Okay, we will talk about indexing in the next class when we actually start to do the hands-on. It will become clear why it's important. Okay, but let's talk about DNA mapping very quickly. So we had already motivated the problem of DNA mapping, which is there are 2 ways to do it. One is you have a totally new DNA sequence and you want to put together what does the actual full DNA sequence look like. And the way to do that is by doing what's called assembly. So I can shear my DNA and then do a lot of them such that I can try to put this entire jigsaw puzzle together without having a reference map. That's called the assembly problem. The mapping problem is where you're given the reference map because somebody has done that hard work, for example, the Human Genome Project, and all my task is to figure out where are these short fragments actually coming from. And we're going to focus on this because this is the easier version of looking at things. So this is the overlapping problem. This is the mapping problem. I'll define it formally. When you first do reads, you can try to figure out what are the overlaps between the different reads. These are different reads. If I do an overlap, I can try to assemble the sequence. So this is your assembly problem. How do you put things together such that you get the full sequence? The mapping problem is, however, other way around. You've already assembled the problem and now you're given new set of reads. You figure out where did it come from. Okay. Okay, so now comes this part which we promised in the first lecture, which is how do you going to do it in a very, very fast fashion. So, right, this course is also about teaching algorithms which you can do very fast and come up with newer data structures which allow you to do this very fast. So, let's talk about some ideas. How will you solve this? So, what you're given is a billion base pair reference and now this is part 2 of the roller coaster. So this will become confusing before it gets better. So just bear with me. Okay, you have a billion base pairs, which means you have some sequence of A, C, D, G, and so on. I give you reads, right? There are like maybe millions of 100 million reads. How will you very quickly tell me which part came from where? And we have studied algorithms to do that. So I don't know where this came from. I'm drawing it here, but it could have come from anywhere. How do I tell? What is the crudest way to tell where it came from? Okay, so I can take this piece and then I run what? What algorithm do I run? Okay. Simplest, crude. Hash mapping, I'm not taught about hash mapping yet. But good idea. You can do hashing. But you have studied some algorithms, right? Which algorithms have you studied? Which, so I can take this and I can scan, but how do I scan? Like, how do I tell whether it's aligning or not? One by one. So where did we use that? Smith-Waterman. We did Smith-Waterman, right? So it's a local alignment problem, right? Does everyone see why it's a local alignment problem? Because I don't have to align this to ends. I'm just looking for which mapping, which particular part of it gives me the best alignment. What was the complexity of Smith-Waterman? Let's call this length L, and then let's call this each read a small length L. So what will be the complexity of this? LL, right? And let's call these N reads. Okay, extremely large number, right? How can we make this better? Okay, now, yeah. How can we make this better? Yeah.
First, we can break the reference unit into smaller fragments and index each one of them, and then compare these things with them.
Okay, and how will you break? Like, at what point will you break? Let's say we break at 100. We break at the same length as L, maybe, right? We can break this at length L. Okay, so we create lot of L sequences such that there are L by L number of reference fragments. Okay, now what do we do?
Compare each of these
Okay, so again, this is one fragment.
after indexing
How do you index? How? How?
like zero,
How? These are buzzwords, but how? Good. These are all correct. These are the right direction. But how do you store them? So let's say example. Okay, let's say, this is the example. Okay, now, yeah. Okay, okay, good. Okay, fine. I think that's what you were. Was that also your idea? Your idea also is similar? Okay, so, okay, good. So let's say, so there are a lot of fragments, let's say like this, right? So you're saying I will take the common part and I will store that these are the lookups that can happen. And now how does it help? Now where do I go? I go to the read. So this is at the fragment level, right? This is at the reference level. How does it help me with search? Okay, so the indexing is fast, so I can index by AC. So let's say if I take this read and the first two bases are not AC, I will drop it right away. But if it is AC, then rather than searching through all other places, I'm going to only search here. Okay, and how approximately how much will it help with? Okay, so let's see this. This will be reduced. Okay, so but still, what will be the order approximately? So this remains, n remains. What about this? Does this was LL, right? Does it go lower or will it remain similar? It will go somewhat lower, right? I think seems it might go somewhat lower by a order of what? So I don't know, right? I don't know. We can calculate, we can take the worst case scenarios, but it will go less by some order of x. But will it still be n cube? or L cube, or will it be still same, right? Like you can get that feeling that you're still doing a lot of comparisons while you have reduced the overall space, but you're still being able to do this at scale. What want we do able to do this at scale? So we will study how to solve this problem and how this problem was solved. Okay, so this is the formal definition of the problem, and we did the version of the brute force. This is called brute force because that's the most naive way to do it, right? And if you do a total computation, even with a read length of a million reads, 100 read length, it's the order of 10 to the power 12, right? Which is extremely large. So the question to understand now is, can we do better? The first way to do this is to use a structure which is called tries, right? The reason our method is slow is because we need to search the genome again and again for a pattern. But if we can somehow break this particular pattern and store it a priori, we don't have to keep looking again and again, right? So for every read, I'm doing a similar computation. So if I can somehow know the patterns that exist in my query or in my reference, I can make the lookup go much faster. And we will see, this is very intuitive. What you said is also kind of what is actually implemented. So we can see how to actually formalize this to some extent. And that's done by something called tries. So what is a try? It has a single node with in degree of 0, which is called the root. Once I draw it, it will become clear. Each edge represents a single character. So it's a data structure where there is one single root, then there are edges. Now when I write an edge, each edge represents a character, a single character. Edge leading out of a node have distinct labels, right, which is clear. For example, if this is A, then from my root node A, root node 0, I have an A character which explains this. Next, I have each path from the root to the leaf represents one suffix. We will see what the leaf here is, and path from root to leaf or node without degree 0 spells out a string from a query. Okay, so lot of jugglery happening there, but let's see what this is, right? So in my case, I can mark the end of it as a dollar sign, which means that the only string that this particular tree or try is representing is A. But I could have also done, or I could have a sequence where I represent this information. Let's say my sequence is ATA, can be represented as simply ATA and followed by a leaf, which is a dollar sign. Okay, we will store our data in this format where each node, each edge spells out one particular single character. Okay, for an example, if you have these words like ananas and antenna, banana, bandana, nab, nana, and pan, you can already see there is some pattern which is similar. What is that pattern which is similar? There's some version of AN coming or ANA coming, right? So if I draw the corresponding try structure of this, if I read from the root to the leaf structure, I can read the entire word. So in this case, A-N-A ananas. This is your first thing. Hopefully this is very clear. Each single edge is this thing. Now if I have to I've created this try first. There's nothing else existing. Now comes the next word and. So I start from A, N. This was already constructed. So this is my D. Right? So do you see already what's happening? You're able to sort of figure out what are the commonalities just by traversing this graph. Then comes your antenna, which is the third word. And again, A and N is shared, you go deeper here. Next comes banana. Now I cannot start here. So I start a new node, B, and then I draw the full thing because there is nothing else existing. Then comes bandana. Now BA and D, BAN is common. So this forms a different tree at this particular point. Similarly, there is nab, which is the new word. There is no tree here. So you form the N version starting from here, and similarly pan. Okay. How do we use this for pattern matching? How is this useful? Okay. Yeah. Okay. Correct. Okay. So you can see that if I want to search something, let's say I want to search tan. How many searches will it require me to do tan to search whether there's a word called tan? TAN. So all one search. All I go here and I know that T does not exist. I don't even have to proceed, right? And that's the exact idea behind searching for a try. So if I have given a word like tan, I can now, which is in the genome, for example, you have a read which spells out pan. If I want to search it, I go there and I look for whether this particular thing is spelled out as it is if I traverse the graph. So the first thing that I will do is I'll search for P. Yes, it occurs. I go next, and so on. Right. So here I've reduced the overall search space because a lot of my patterns are already summarized here. Every data that I had is in some sense being summarized in my overall format. So I can use it for doing efficient pattern matching. Yeah.
If we were to do a pattern matching for how would we proceed?
How do we proceed with this, right? So for this example, what I will do is, it will become clear in just 2 slides, like how will we use this for this structure. But just to spell this out, right? Like if I gave you these read structures, you can construct a similar try structure using the read data here. You can do it on the reads. You can also do it using what somebody said, the suffix version of it, right? So what is a suffix? So if this is my genome, if a read has to occur, it has to be a legible suffix of my genome, right? So what is a suffix? It's something which, if I start from here, it takes me towards the end. So for a read to happen to be coming from this genome, if I make all possible suffixes of this genome, it should be part of one of the suffixes. Does that make sense to everyone? So if I take my entire genome and if I have to show that this read is part of, if it maps somewhere, it has to occur in either this suffix, which is going from here, or even a longer suffix. It is going to be present in one of the suffixes of your genome, right? Why suffix? Because ends are good and we like to anchor on the ends. So that's what we're going to invert the structure and look at how do we do it. So this is just the algorithm spelled out as to how do you do a prefix match. If you have to look for pan, you can look for that particular prefix by just traversing this particular try here. Okay. I can use it for doing multiple pattern matching. I want to find out all possible matches of a given string over the genome. You can start by first looking at that particular symbol in the text and then chopping off every next iteration to it, right? So let's see an example and become clear what it means. So given we have discussed about suffix try, can you tell me how will you check if a given string S is a substring of T? What we drew here is a try. How will I test whether a given string S is a substring? What is a substring? It occurs somewhere in T. How will I check this? Okay, bottom to top. But often when you're traversing, you don't know the last, right? You have stored this in the memory. So you'll have to traverse the graph all the way to know where the ends are, right? So we'll just do this example and okay, we'll just do this example and it'll become clear. I want to check whether S is a substring of T. So how do I do this? I will follow the path for S starting from the root because that's where things begin. If I keep going and if I find it, if I don't fall off the tree, then it's a valid substring, right? So in this case, BAA, if I search for BAA, in this case, I keep going and that means this will occur somewhere. It's a substring. However, if I search for BABB, I keep going and I land up at B, but after that there is an A, right? So this cannot occur as a substring. of S. Okay, the reason we are doing this is because we will start to do read search. So this helps us determine at what point should we end sequencing, should we end actually searching, right? So it helps you compress your space. Think about the other two cases. Okay, let's very quickly discuss it because it's intuitive. How will you check whether S is a suffix of T? What does it require to be a suffix of a trie? Yeah. Yeah. It needs to reach the end, right? If S is a suffix of T, it has to land up towards the end. A is a valid suffix of this tree because this is where all of it is ending, right? Very good. Count the number of occurrences. How do you count the number of occurrences of a substring in this tree? Focus on this, or better focus on this graph. We can do this example here, let's say. I want to count the number of occurrences of AB, for example. Oh, sure. Let me escape and then zoom in. I want to count the occurrences of AB. Okay. So AB, I have to search A first, then I search B, and I get at one location. So at max, how many times does it occur? AB occurs.
So maybe the node itself can store the number of ABs.
So you can store at each point, you can store the number of nodes that you're going to get. The outward edge that you're going to get from each node tells you how many times you see it, right? So in this case, if I take ABA, for example, that is easiest to see, ABA will have two occurrences at least, because there is definitely ABA, and then there is ABAA and ABA, which ends there, right? So I can count the total number of outward edges which are remaining to be traversed, and that tells me how many number of times it will occur. Okay. And what about the last question, which was, how do you find the longest repeat in a particular sequence? What is the longest repeat? Longest repeat a sequence, which means that particular substring of the trie will have to be repeated most number of times, and it's also the longest. You can forget about the most part, but it is the longest thing which repeats.
See the node which is furthest from the root. That will be
Farthest from the root, okay, and
yeah. So you can
distance from root and the. So what is a repeat? It's repeating in that sequence multiple times. So if I have given you, for example, see if I have an example. Okay, so let's take this particular tree for example. What is that particular string which you think is repeating, which is the longest thing which repeats? What is that pattern which you'll see repeating the maximum number of times? AABAA. Why? That seems to occur only once, right? Okay, here also, okay. And in the last. Okay, fair enough. How do we find this? Okay, so the one way to do this is to look for, you can define a particular endpoint here. In this case, this endpoint is given by your dollar sign. For the longest suffix, for the longest thing which repeats, you are looking for a region which repeats multiple times, right? Which, yeah. So in this case, you will go to the deepest node, right? In this case, for example, this is ABA, such that it has the maximum outgoing edge overall. So in this case, ABA, while AABA is not the starting, right? It's not something which will start your overall string. Here you're looking for at what point everything, that particular substring is being repeated multiple times. So if I go to that node where I see the maximum depth happening downwards, that is going to be a repeat, not AABA. The reason AABA is not a valid repeat is the way we set up our sequencing is starting from here and ending here, right? For something to be repeated, that particular substring has to occur at multiple locations, right? In this case, ABA is the one which has your common structure, whereas AABA is something which does not occur as a block in multiple places. Does that make sense?
Why are we taking only those substrings that start from the root? Isn't the down the line when there are those
Because
substrings are
these are all possible substrings of your trie, right? These are all the possibilities that exist in your trie, which is what you're laying down from the root. Okay, and ABA by itself, for example, never occurs in the structure of the trie. It starts from when you create your trie. This pattern is being lifted from all the sequences that you have access to, right? So the start and the end, in other words, are already mapped. These are structures which you are picking up to create the patterns that exist. For something to be repeated multiple times, there has to be a common start and a non-common end. In this case, if I pick up AABA, right, which is this particular pattern, it occurs here, but it is not being shared. Had it been shared, I would have common edges outgoing through it. While it occurs in parts, the prefix part of it is not being shared, right? So if that particular part is not common, this repeat structure does not entail, because there's no common start at which you have your bases which align.
Won't it cause some kind of issue? As in, you are giving priority to the prefix
Yeah.
than suffix.
Yes, because that's why we ended up with marking these things with a dollar, so that I know where the end is. Otherwise, your pattern is all over the place. You can align to whatever location you want if there is no end. So you should, in other words, right, you should think about this sequence also to be a prefix of the all the possible matches that can happen. Now, if I pick up AABA, here it will match because it has an end to it. But if I pick up AABA, I can never reach that. In any of these sequences besides this, I will never be able to even start looking for that particular match, because it's not a valid prefix that happens to be. Does that make sense? Because it never existed as one of the nodes that I can traverse itself. So it's not something which is being repeated multiple times. Okay. Okay. So in this case, for a string to end, so the other way to see this, right? If anything is common, you will have it share a common structure, and that common structure is something which happens here, which is having a maximum depth, and that depth happens to be 2 here, which means that at any point this particular part ABA is going to be repeated, in this case, for example, twice, because it has that particular prefix structure, which is what the trie is based on, rather than taking, let's say, ABA, or which happens to be here, but it's not a valid start for this. So if I start searching for ABA, I will never be able to take this route. But in this case, this particular route is a possible route for all of them to take. Okay. Okay, so when we come back on Thursday, we will try to even further reduce the storage. So what you have seen is a version of tries, and it takes into account each edge. If you have to store this in your disk, it is going to take a lot more memory, because each edge you have to store one single base. While, can you think of a way to compress this tree? How will you compress this? It's too long for you to traverse. Yeah, something of that sort. You can reduce this, and that becomes a suffix tree. And we'll come back and finish first suffix tries, and then we'll make a suffix tree and a suffix array out of this. These are what's used for mapping, DNA mapping in the real world. Besides one more structure which we're going to study, which is called the Burrows-Wheeler transform. And when I first studied about Burrows-Wheeler transform, I was like, this is one of those algorithms which can never work because it's extremely unintuitive. I mean, I still find it very unintuitive to get it the first time, but it's one of those things, once you get it, it's like, of course it works. Okay. Okay. Thank you, and sorry for extending it.